How many of you own a smart speaker? Do you ever worry about it listening when you don't expect? Do you worry about what happens when your voice query is transmitted to the cloud? For me, I'm not worried about surveillance. Some hacker would have already identified a backdoor by now if there was one there. But surveillance isn't the only thing worth being concerned about. When you interact with the actions of your smart speaker, a lot of information and metadata flows from your machine to a server, somewhere. Today's episode explores one way in which that data can be used for targeting.
I'm Rajan Udwani, and I'm an assistant professor at University of California Berkeley. So I'm in the Department of Industrial Engineering and Operations Research. So that's both my research and teaching revolves around operations research. I guess operations research is a field that's really spans a lot of different areas, and it's really about using tools from optimization, statistics, data science, machine learning, etc. to try to solve real-world problems. My own specialization within OR is on the algorithmic side. So I really like to think about designing and analyzing algorithms for optimization problems, especially when there is some natural uncertainty in the problem.
As you pointed out, data science and operations research certainly have a large overlap. Maybe even some people could say it's the same thing, or, it's a very strongly overlapping Venn diagram. But I've noticed operations researchers seem to have, generally speaking, a much better fluency when talking about optimization problems. Could you expand a little bit on that? What are some of the tools you use and how you apply them?
Optimization certainly is one of the, bigger focuses in OR, at least from my point of view. It all arose out of linear programming and mathematical programming, which is a very general way to model optimization problems, that you have an objective, you have a bunch of constraints, and the kinds of tools, as broad as really the kinds of problems. So there are, of course, tools centered in mathematical programming. There are these general tools like solving integer programs, and more generally mixed integer linear programs and with nonlinear objectives. And then there are tools that come from the kinds of problems that maybe we'll talk a little bit about today, online optimization. Then there are tools from sort of classic understanding of combinatorial optimization and many other sort of problems over the years that have led to their own specialized ways of thinking about optimization.
Well, these techniques could be used in just about every industry. What got you first interested in digital advertising?
My interest in the ad space, or for the Adwords problem, really arises out of the fact that one of the classic problems in online optimization has deep ties to the ads problem. As I mentioned at the start, I'm interested in algorithm design for optimization under uncertainty, and one of the uncertainties in ads that has a very close connection with these classic problems in online optimization is the fact that there are different kinds of queries arriving over a period of time. And when, let's say, a platform wants to make some decisions about ads, it doesn't really know what's going to come in the future. Future is unknown, uncertain. So that's really where my interest arises from. It's more from the mathematical connection with these problems that I'm interested in.
I think listeners will know that a lot of these are auction-based systems and have some sense that advertisers are making bids, and the visitor to the search engine is the user who's kind of getting an impression, and that there's the platform, or Google in the case of AdWords, who has to provide the auction mechanism. What else should they know about that process to understand these things?
One could think about auctions sort of by breaking it down into two parts. One's the pricing rule, and the other one is the allocation rule. When I think about the AdWords problem from the optimization point of view, or what we are going to talk more about today, is keeping one of these things constant. So let's say that our pricing rule is fixed. It's given by, if you want to sort of say one more word about it, first price auctions, let's say. And then we are going to focus really on the allocation, and that's where the optimization part comes in. The allocation here is that, you get a query. Let's say that there is a pricing rule that we have fixed. Now, people make bids. These ads, there'll be bids, and then which ad do we show? So the platform gets to decide which ad to allocate, if any, to this query. We really want to figure out quite carefully how to optimize this allocation process, because of the fact that this is not the only query we'll get. We'll possibly get many, many queries, and we don't really know what kinds of queries we'll get.
So when Google is conducting this auction, they're going to apply optimization strategies. Is it as simple as they just want to maximize for profit?
That's one of the objectives one can think about, which is to say that Google wants to maximize the total amount of budget of each advertiser used, which corresponds also to maximizing profits. There are other objectives. They could maximize the total number of clicks they get or total number of ads they show and so on. Each one, though, has this common inherent uncertainty that they need to think about as they figure out what's the optimal allocation. That sort of interest or the queries that I am going to get in the future, they will not be the same as what I'm seeing right now or I've seen in the past. There is this matching problem that I want to solve in order to make the optimal allocation, regardless of the objective. Because I don't know the future instances, future queries, really, I have to be careful and really think hard about what allocation I want to make right now. If I just make a greedy decision that does the best right now for whatever objective, that really need not be the best way to go about making allocations.
So yeah, this seems pretty challenging. I don't want to be overly reductive, but I'm thinking of, like advertisements for umbrellas, and on a day it rains, maybe there's more searches and more purchases. And Google didn't necessarily know it was going to rain. So if all the ad budgets were spent earlier on, there would be a loss of opportunity there. Is that too simplistic of a use case?
Yeah, that's certainly one of the ways this thing arises. And I can give you another example. So what you pointed out, Kyle, was one way in which this kind of an uncertainty is important, that you want to try to spread your budget and you don't really know when it will be consumed, so to speak, or when's the best time to consume it. Another example which captures this sort of inherent heterogeneity in queries is the following. Let's say that there are two ads. So there is a pizza store that wants to give ads on Google, and then there is a delivery service that wants to give ads. Both of them have, let's say in this stylistic example, a budget of just one ad. So they'll just bid $1 in this hypothetical scenario, both of them. There is a query coming in. The first query is somebody searches pizza near me. Now both this pizza storefront and the delivery service are interested in this ad, in this query, so they'll make their bid. What Google doesn't know at the moment is that the next query may be grocery deliveries. The delivery service is interested in that query, but the pizza storefront isn't. So if I knew at the moment that I'm going to next also get a query on grocery delivery, I could actually figure out that the right thing maybe to do is to show for this pizza near me query the storefront, because then I can use the budget of the delivery ad and show it to the grocery delivery query. Since I don't know that in the future I'm going to see grocery delivery, how do I go about still making a clever decision here? So this is something that is challenging in these problems.
Yeah, I think there's maybe two broad ways to look at it. One is you can try and do a lot of forecasting, guess about what queries are coming up and this sort of thing. Otherwise, you could maybe just embrace some approach and say, here is my algorithm, and I hope it has nice properties. Do you have any insight into the way it's actually implemented?
My understanding is that both of these ideas are kind of hybridized. So the forecasting approach leads to models that, at least in academia, we think of as sort of stochastic arrival models, where I have some distributional knowledge about what future queries will look like. I don't know exactly what they will be, but I have a distribution. And I can use this knowledge to make better allocation decisions right now. And the other approach says that, what if queries are extremely hard to predict, right? Some major event happens and then that completely changes and forecasts are not valid anymore. So there's the adversarial approach that will say that I have no clue what's going to happen in the future and tries to develop algorithms that will do well even in such scenarios. And what I've been told is that these real systems at search engines try to really do both these approaches. They try to smartly figure out perhaps which is the right approach at a given time point and follow the suggestion of the respective approach.
And do you have any anecdotal knowledge or even your own instincts about how good these models are? Is it fairly loose, or can we make good predictions about this sort of stochastic system?
At least at a high level, my understanding is that in ads kind of spaces, predictions can be hard, though they do make predictions and do get a lot of useful information out of it. There are other domains which also share the same kind of similar mathematical structure, like reservations on airline systems, where predictions are perhaps a little bit easier than in the ad space. So both these approaches, I think, have seen use, and the typical use case is that you try to figure out the right way to combine these approaches.
And what are some of the general algorithmic approaches? How do, whether it's the naive first way people try, what are some of the general sorting, ranking decision methods?
I guess the most natural, maybe one can call it the naive way that I think you would come up with if you really sat down, I gave you the model very clearly and you were thinking about what you want to do, would be what's called the greedy approach. So remember, we are thinking about just allocation and we have abstracted away all the pricing details. So when there is a query, we figure out which ads are relevant for this query. That's based on the keyword being one of the targeted keywords of the ads and so on. And then these ads are all going to make bids. So the greedy approach will just say pick or show the ad that has the maximum bid as long as there is still some budget of that ad remaining. That's it. So each time you get a query, look at all the bids, pick the ad that has the highest bid subject to budget being available for that ad and show that ad. This approach is perhaps unsurprisingly not the best approach, at least in terms of analysis, theoretical analysis, trying to understand the performance guarantee of this algorithm. One can show that this algorithm would only in some sense get you 50% in the worst case of what you might get if you knew all the queries a priori. So there is this information gap that you have, you don't know the future, and this greedy strategy gets you still 50%. One can do better than this, and that was one of the sort of seminal results in this area. So one of the strategies that can do better than this and in fact achieve the best possible theoretical performance does something very intuitive. So what it will say is, well, I want to be greedy, but at the same time I want to look at how much budget is remaining in a more careful way. So if I have two potential ads, I don't just want to look at their bids for a query, I also want to look at what fraction of the budget remains for each ad. And for an ad for which there's very little fraction of budget remaining, I'll shade the bid a little bit. So I'll compute these shaded bids or reduced bids for each ad and then pick the ad that has the highest shaded or reduced bid. And this shading happens in a very careful way. It's a function of the remaining budget of the respective ad. And turns out that if you shade in the right way, you can actually do substantially better than greedy, even in the worst case. This kind of an idea of shading or considering these reduced bids has, as far as I understand, made important sort of contribution. Thinking about this idea led to some of these high-level ideas like throttling and bid shading that are, I think, used in modern-day search ads.
So it makes sense that, we didn't do the derivation, but to say that 50% is the efficiency for greedy, it's intuitively appealing. I can trust that there's a mathematical proof there that listeners can find in the paper. And then obviously there's a ceiling here. If I had perfect knowledge of the future, I could come up with the optimal solution because I know what's going to happen in advance. I can do no better than that. But this new approach with proportional bidding to the available budget left, where does that put us between, this lower bound of greedy and this theoretical upper bound of seeing the future?
Right. So the approach that I was mentioning, which really looks at the remaining budget, that's actually sort of a classical approach from 2005, let's say, that basically gets you 1 minus 1 over e, which is like 63% in terms of the theoretical performance. That's the best possible. So you can be very, very smart. You can figure out many, many complicated strategies. None will do better than this bid shading approach in the worst case. Now, the approach that I have in my paper really tries to relax one of the central assumptions in this setup and then ask the question again, can we do better than the naive greedy approach?
Right, so we already have kind of a hard problem. It was enough to say I know all the bids and I know the budgets, but I just don't know the future. How can we make this more difficult?
A way to make problems more difficult, I guess, in some sense, let's say you know even less. So what if you didn't even know the budgets? So all you knew was that, you will do your allocation at some point. If you run out of budget, which you don't know, you will just get all of a sudden notification. Okay, this ad is out, its budget has run out. But until you get to that point for any ad, you won't have any idea what their remaining budget is. So when you don't have this knowledge of budget a priori, the problem becomes interesting.
I don't have an intuitive approach, like reinforcement learning comes to mind, but it's not obvious what's the right methodology. How do you approach this relaxed assumption? Thanks to our annual sponsor, Weights and Biases, the developer-first ML platform. Weights and Biases is an enterprise-grade platform that gives you experiment tracking, dataset versioning, and model management. Their solution integrates with TensorFlow, sklearn, XGBoost, Hugging Face, and literally every other framework I could think of. Integrating with your model training process takes just a few lines of code. And there's even a nice live notebook on their site that'll show you how to get it going. Once your machine learning code base or notebook is wired up, you've just unlocked the next level of productivity. The Weights and Biases platform collects, aggregates, and beautifully displays all of your key metrics and telemetry so you can track your model training in real time and compare different runs. Have you ever had to screenshot a matplotlib graph that you drop in an email or in Slack to show your boss the results of your work? That's like serving a gourmet dinner in a cardboard box. With Weights and Biases, all of your collaborators can see the results of different runs with an idealized interactive suite of tools. You no longer have to be the single source of truth for your whole organization about how the model's doing. If you're on or leading a growing team of machine learning practitioners, you need to investigate if Weights and Biases is the right solution for you. Get started at wandb.me/dataskeptic and mention us when you request a demo. Hi, I'm another one of those podcast ads that you've managed to tune out so effectively. It's okay, I get it. Listening to podcasts comes with some degree of ad fatigue. But today, you need to listen up because I'm here to tell you about ad fatigue's sinister cousin, alert fatigue. Did you know the average company receives 11,000 security alerts each day? How can a security team stay on top of the most critical threat risks when they can't find the signal in all the noise? Well, they can't, which makes it easy for IT teams to fall victim to alert fatigue, making your company dangerously vulnerable. So you have two choices. Buy all the tools you can until you've made your security operations overwhelmingly complex and totally ineffective, or you can run with the pack. Arctic Wolf is the industry leader in security operations solutions, delivering 24/7 monitoring, assessment, and response through their patented concierge security model. Arctic Wolf works with your existing tools and becomes an extension of your existing IT team, and they never get fatigued. Got your attention now, didn't I? Visit arcticwolf.com/skeptic to learn more. That's arcticwolf.com/skeptic. I mean, I don't have an intuitive approach, like reinforcement learning comes to mind, but it's not obvious what's the right methodology. How do you approach this relaxed assumption?
Right. So one could still continue to do this kind of greedy thing, which says that I'll just pick the ad that has the highest bid and show it. If it turns out that you ran out of budget at this point, you will just get this notification, okay, you've run out of budget. And it turns out that that's not too damaging. You can still get 50% with this greedy approach, which completely ignores the budgets. Other approaches that maybe use some kind of learning, maybe they could be applied in some way. But then the key question really becomes, this budget that you don't know, how is it varying? Why is it that you don't know it? Maybe there isn't a natural way to learn it anyway. The approach that I take in the paper is to say that, okay, I know nothing about these budgets because they could be part of some complicated real-time optimization problem. We could still do better than greedy, it turns out, but by randomizing our decisions. So far the algorithms that I briefly mentioned, greedy and the other bid shading algorithms, they are deterministic, meaning that if you give some input to the algorithm, the output will be the same each time. Randomized algorithms, this is not the case. So I can give the same input to a randomized algorithm, it might give me different output at different points of time because it's using randomness in its decisions. So this randomized algorithm that can still do better than greedy even without any knowledge of budgets will still follow this high-level idea of shading bids, but it will shade bids in a random way. And if you shade bids in the right random way, you can do better than greedy.
This seems the onset very surprising to me because if they're just random budgets, it seems like they wouldn't correlate with the true budgets. So there's no value, there's no information there to work with. How does the randomization? How can I exploit that mathematically?
The bids, the budgets are unknown and the bids are not random, right? Bids are something that the advertiser ads will come with the bids for each query. And now we still rely on the bids, but perturb them randomly. So if you think back again to this idea from a previous seminal work that you shade the bids as a function of the remaining inventory. If I have low inventory, I will try to protect that ad and reduce its bid. So now that we don't know the budgets, we will do the shading randomly. So I will reduce each bid by some random amount, but I still reduce them in a multiplicative way. So let's say if I have a bid that's 10 and another bid that's 5, I'll shade the first bid randomly. So I'll multiply that 10 by some suitable random number, multiply the 5 by another independently chosen random number. But these 10 and 5, I still have this factor of 2 difference between these two shaded bits, thanks to the initial bits being different. So it's not purely random, it's randomness in proportion to the bits, so to speak.
Do we then assume that the budgets are proportional to these randomized bids, or how do we get to what a budget would be?
Right, so budgets can be arbitrary. We assume in this setup, which is typically also, I believe, true in practice, that the budget of an ad is much larger than any individual bid. In fact, many times any individual bid. So the total budget we still assume, even though we don't know it, is, let's say, 100 times, just to give you a numerical example. But I don't know. It could be 200 times, it could be 1,000 times. Budgets are arbitrary. They are just much larger than individual bids. And I do know the bids. I don't know the budgets.
Gotcha. So then how you also don't necessarily know the real queries that are coming in. How can you evaluate a hypothetical algorithm like this one?
Right. So that's where I guess when at least we are analyzing the performance in theory, we have this very successful and popular idea, which is to consider the performance in the worst case. I don't necessarily know what kinds of queries a real system might get, but I can figure out how this algorithm would do if there was an adversary out there really trying to make sure that I do a terrible job at allocation. So I can look at this worst case and try to show that my algorithm will have such and such a performance even in the worst case scenario. So that's how we sort of come up with these numbers, that 50% or 63%, or in case of this randomized algorithm, something like 52.2%.
Gotcha. Could you give an example of that adversarial behavior? If I'm an advertiser who has bad intentions, what sorts of sneaky things might I do?
So it's actually less about, I would say that an advertiser is adversarial, but more about that the future which I don't know could be adversarial from the point of view of my algorithm. So if I could go back to my to the small example where I said that let's say we have two ads, one ad is a pizza store and the other ad is a delivery service. If you think about this scenario where if we get the first query could go to either of these ads. Both ads like the first query. But the second query, which I don't know at the moment, only goes to one of the ads. When you're trying to solve the allocation problem, you just see the first query, right? And you need to make a decision right now. And you need to pick one of the two ads to show. Well, you don't know which one to pick because you don't know the future at all. So you'll pick one of them, let's say, and you end up picking the wrong one because it turns out that next query is in some sense adversarial. It's a query that will only go to the ad that you have already used the budget for. So you could only show one ad, even though you got two queries in this scenario where the next query became more picky.
It's like perpetual bad luck.
Right. Yeah. Yes. And it turns out that some of the worst instances in these kinds of problems end up being ones where queries are increasingly picky over time. And you never know at a given moment which one is really going to go off trend for future queries. So you do your best to figure out and balance all the ads.
Well, I was wondering if we could return to some of the efficiency calculations. What you calculated is doing better than the greedy strategy, though admittedly not as good as the approach that uses bid shading when we knew the true budgets. Of course, we're more blinded in this situation. We couldn't possibly achieve the same results. But where do our results come from? How is it that even lacking the budget information, is there some core kernel of truth of what we take advantage of to beat the greedy algorithm?
So I guess first thing is just a caveat that at the moment it's actually an open problem to figure out that if you can do as well as the deterministic bid shading approach even without knowing budget. So even I don't know the answer to whether you can do as well or whether you can show that you can't do as well. So coming back to your main question about where does this however small gain on top of greedy actually come from? So I think that's really the power of randomization. So in fact, one can show that if you use deterministic algorithms and you don't know budgets, you cannot beat the performance of greedy. Now the reason that's interesting is because remember that this classic approach of bid shading is a deterministic approach, which gets you 63% and has made, I believe, significant impact on practice. When you don't know budgets, you actually cannot use not just that approach, but no other deterministic approach will improve on the performance of greedy. So randomization is really this tool here that I think allows you to do better, even though you don't know the budgets.
And you've touched on this a little bit, but I'm curious if we could explore the commercial applications or the settings in which this is a more appropriate way of managing things. Like in Adwords, you're required to give a budget, so I guess people are used to it and they can just do it. But there's got to be other areas that it's truly the case that a budget's unknown a priori. Do you have any examples of those?
So in the ad setting, some potential application, again, there will be many challenges to something like this, could be that if these budgets are being decided in an automated fashion by the platform, let's say, which is managing many different campaigns for an advertiser, there may be some potential for not fixing the budget for the day a priori, but adjusting it in real time for the benefit of both the advertiser and the platform. Of course, changing something like this, which is so fundamental to search ad platforms, may have a lot of other challenges. So I don't know if that would necessarily, in the end, lead to a better bottom line. Other places where sort of not knowing these budgets a priori could be useful, for instance, if you're in a setting where there are two types of traffic. One type of traffic that is in some sense coming offline into the store, and then there's the online traffic. It turns out that this is again a case where you really want to focus on the online budget. So you want to subtract away all the offline traffic and want to focus on the remaining budget because that's better in terms of allocation. But you don't know how much the offline traffic will be, what proportion of budget will it take. So if you have a budget oblivious algorithm that's doing the allocations online, it sort of just bypasses the problem completely.
Work like yours may be motivating a change in the way existing systems work. I know these are, a system gets pretty entrenched once it's launched, but are there any theoretical motivations that would suggest we migrate to a system like this?
That's a good question. So given that there are many sort of moving parts, there are small examples that one can at least think about to say hypothetically that this could be useful. Going back, I guess, to the ad setting where a platform allowed real-time budget adjustments, it might be able to, for instance, figure out. So there's a platform that's managing two different campaigns for some organization, let's say. If it realizes that for one of these campaigns, this is an interesting day. So there are a lot of queries coming in for that kind of campaign, but not so much for the other one. It could rebalance the budget during the day. And this could have usefulness and could lead to a better allocation overall, a better usage of budget for the organization. But having said that, I guess, there'll be other things that one would really need to think hard about if one were overhauling the system. What I can say is that the kind of algorithm, this randomized algorithm that does do better than naive, greedy strategies even without knowing budgets, is very, very scalable. So it's not an issue of implementing it. It's easy to implement. But whether after looking at all the moving parts, it would really need to some improvement, that's something that I think unless one really tries it out and really understands how everything else would change, it would be unclear if it would improve the bottom line.
Well, I'm curious, what's next for you? Is this part in a series of research things? Is this an offshoot, or how does it fit into some of the things you're working on now?
This problem and this kind of uncertainty in future, this is something that actually is inherent in many different applications. So there is this common underlying, let's say, meta problem, which is about how do you allocate resources when the demand for resources is sequential and coming in an online fashion. So that's an area that I'm very much interested in, the area of online resource allocation. I have other works in this area at the moment, not necessarily perhaps related to ads, but with the same high-level goal that you want to try to figure out interesting ways of making allocations when you have uncertainty in the future and maybe other complications due to new practical applications. And you want to design algorithms that are scalable and also do well in a theoretical worst case manner.
Are there any other mechanisms we might add to the auction platform that could allow, either the advertiser to send us more information or for us to infer something, but additional techniques or rules of the system that could allow us to better optimize?
So at least in the space of what we were discussing, that there's this uncertainty in future and therefore you modify the bids or shade them a little bit. There are, I believe, many different techniques. Two of them are called, one's throttling, the other is bid scaling or pacing or bid shading. Both of them have connections and in some sense were really inspired by some of the classical work on this bid shading idea that we talked about. Throttling, for example, is a technique that tries to, for each auction, so anytime a query comes and there's the auction, will limit participation. So it will only randomly pick a subset of ads and only allow those to participate. The way this is connected to the algorithm that we talked about is that that algorithm looks at remaining budgets, and if something is low on budget, it will really reduce its bid. So throttling is a more extreme version, which will just say that, okay, either you're in or you're out. So it's like a binary version of that idea of reducing the bids based on remaining budgets. Another idea that's also used to sort of manage participation, what's called bid scaling or pacing. And there the idea is that we'll reduce the bids, which is very similar to the algorithm we talked about. But if an ad wins the auction, they'll also pay the reduced bid. So when we were talking about the algorithm, the amount that the ad actually pays to the platform, that does not change. That is equal to the bid. But in this bid shading, bid scaling idea, both the bid is reduced, but then the payment is also reduced and the same as the reduced bid. So these are two high-level ideas that I believe are implemented to better control in this budget constraint setting, sort of sequential auction setting, the utilization of ad budgets. And they arose really, as far as I understand it, or were inspired by this classic paper on Adwords.
I'm also curious if you would be willing to speculate a bit about the future and where things are headed. Do insights like those coming out of your research, are these just going to make it more efficient for the platforms to deliver ads, or might it be that even the consumer's appreciation or experience of ads becomes enhanced in some way as well?
I think these ideas, algorithmic ideas, can be used to do either. So if a business manager decides that my objective is to maximize revenue, they can use such an algorithm to maximize or improve their revenue. If they decide that their objective is, let's say, just to maximize click or click-through rates or expect number of clicks, they can certainly use these algorithms to do better on that. So these algorithms are in that sense moldable. They can help you maximize your objective. And typically, my understanding is that platforms don't just want to maximize one or the other. They want to keep their cash flowing, but at the same time also want to give regard to the long term and maximize user satisfaction. I think it's always going to be the synergy between both of those things, that you want to make sure that you are making revenue, but at the same time not sacrificing on customers and really making them loyal long-term customers is what's going to be the future, meaning try to do the best you can on both those fronts. And these kinds of algorithms can sort of tune to your objective, in at least to some extent.
Well, where can listeners follow you online?
The best way would be either my Google Scholar page or my web page. That's where I put up. I typically tend to put up any of my new papers, preprints directly online, either on Archive or SSRN, and they come up on Google Scholar or my web page very soon after the paper is up somewhere. So that would be a great spot to follow my work.
Yeah, we'll have links to both in the show notes.
Thank you.
Well, thank you again for taking the time to come on and talk about your work.
Thank you, Kyle. Thank you. It was a pleasure being here.
That concludes this installment of Data Skeptic Ad Tech. Join us again next week when we start asking a few questions about smart speakers.
The smart speakers are now being used by millions of people, and we do not understand how they work, like what data do they collect, how that is used, and whether that is shared with anyone else.